Okay, we'll be ready for our next talk. Dr. Samshubro Branyapati talking about, see what it is. It's not come on the screen yet. Yes. Oh, it's here. It's, no, it doesn't. Oh, tight bounds for distinguishability of quantum states under separable measurements.
Okay, so it's a pleasure to be here. And I would like to thank the organizers for their splendid hospitality that they have extended to us. And I'm sure all of you will agree with me on that. And so what I'm going to talk about today is a recent work with Michael Nathanson, where we are interested in quantifying locally indistinguishable states and quantifying distinguishability using separable measurements. And this is a hard problem in general because there are very few analytical results, and I will try to explain why this is hard. We have obtained some bounds, lower and upper bounds, and we have shown that these bounds are optimal in some cases. So what's the basic question? Why people are interested in this problem of local discrimination? The question, a fundamental question in quantum information is, when is global information about a quantum system also available locally? So this is a question which has applications in a wide range of problems of interest in quantum information. So formally, this question can be posed as a local discrimination task, where in its simplest form, I have two parties, Alice and Bob, okay, and they are given a quantum state chosen from a set. They know the set, but they do not know the identity of the state they were given. And their task, or what they want to learn about the state of the system. That is, which state, their goal is to learn about which state information they can access when they're restricted to local operations and classical communication. That's the paradigm of quantum information. So once again, the basic question can be posed as how well we can distinguish a set of quantum states by LOCC. So why is this interesting? This optimal, as it turns out, this optimal local discrimination is only possible for any two pure states, and beyond that it's not always possible. So if I have a set of 3 or more pure states, it's not guaranteed that by LOCC they can be optimally distinguished. So which essentially means that global operations, global measurements, can reveal more information about the state than what you can attain by LOCC, and revealing a new kind of non-locality, which is very different from what is captured by Bell inequalities. And this has found also applications in some quantum cryptographic primitives like secret sharing and data hiding. And I will try to give you some examples to motivate why these problems are really interesting. So one of the examples, widely studied examples, is the distinguishability of orthogonal states, in particular distinguishability of maximally entangled states. And we know that no more than D orthogonal maximally entangled states in D cross D can be perfectly distinguished. Okay, and what is more interesting, that very recently, it's one result last year, which showed that you can find D maximally orthogonal states in 4 cross 4, like 4 maximally orthogonal states in 4 cross 4, which you cannot distinguish perfectly by LOCC. Even more, this year, Cosentino and Russo has exhibited a set of states, maximally entangled states of cardinality less than D, strictly less than D. Another important result is that, so if I give you an orthogonal basis and I tell you that this is perfectly locally distinguishable. That is, you can distinguish the states exactly without any error. Then the set must contain product states. Every state in the set must be a product state. Remarkably, the converse is not true. That is, not every product basis can be perfectly distinguished by LOCC, which gives rise to what you have heard in the last talk, non-locality without entanglement. So here I have a set of 9 product states in 3×3, which cannot be reliably distinguished by LOCC. And it also tells you one more thing, that is, not every separable measurement can be implemented locally. Now, generally speaking, in presence of entanglement in the states tend to be a problem for discrimination. But this is a remarkable result. It shows that sometimes increasing the average entanglement in a set can enable perfect discrimination. So for instance, consider this set. This set contains 2 maximally entangled states in 3×3 and a product state, and this state is not perfectly distinguishable. Whereas, if you replace this third state with another maximally entangled state in 3×3, this set becomes perfectly distinguishable. So sometimes increasing the average entanglement of the set can help you to discriminate the states. So as I said earlier, that our goal is to quantify distinguishability, and preferably we would like to concentrate only on LOCC, that is the class of LOCC measurements. But unfortunately, the class of local measurements does not have a simple mathematical characterization, so we work in the regime of separable measurements. So this is a class of measurements where the components do not have any entanglement between them, but this contains all LOCC measurements as a strict subset. So here is a typo. Actually, just ignore this MAs here, but this one is fine. So what is a separable measurement? Formally, the definition of a separable measurement is, it's a PRVM, and without any loss of generality, I can take that every element of PRVM is a rank 1 element, where every such element is a product state. And now I'm going to define the distinguishability measures. That is, I want to quantify distinguishability under separable measurements, so I need good measures. To begin with, consider this set S, where I have this state psi I, each occurring with probability pi. I have a measurement M, and I have a guessing strategy which simply maps this classical outcome to some state. So what it actually does, so I'm given a state, I choose a measurement, I get an outcome. Based on the outcome of the state, right, I simply do my best guess, or I just reconstruct another state. So in this formalism, you can simply find what is the average fidelity of such a procedure given a measurement and a decoding scheme, which is denoted by G. Now, of course, this definition has nothing to do with whether the states belong to a composite system, whether the measurements are separable or PPT. It doesn't matter. This is a very general definition of fidelity, average fidelity. Okay, regardless what kind of states you are interested in, regardless the kind of measurement. Now, this quantity, this achievable fidelity, tells you that for a fixed measurement, what's the best you can obtain? That is, it is optimized over all reconstruction maps or decoding maps. So for a fixed measurement, achievable fidelity tells you this is the best fidelity you can get for that particular measurement. But we are interested in local discrimination. That is, we are interested in discriminating states by separable measurements. So we simply optimize the average fidelity over all separable measurements and reconstruction maps. And this yields the separable fidelity, which is simply the average supremum of this average fidelity, where the supremum is taken over all separable measurements and state reconstruction maps. So that's one of the measures that we consider. Separable fidelity has been considered by Navascusi in an earlier paper where he showed that numerically you can compute separable fidelity, but it's rather non-trivial in the sense you can have a sequence of real numbers which converges to separable fidelity, that's for sure. And he claims that every element of the sequence can be computed efficiently. And with his numerical method, he gave an example of states, which I will discuss later on, for which the separable fidelity can be computed exactly. But as you can see, this is already a hard problem because it involves two optimizations. And I'm not going to spend much time over here because my earlier speaker has discussed a lot about this. This probability of success is essentially this minimum error discrimination problem. Okay. So just this notation means this is the optimal value of this probability of success over all measurements, but when I have this S here, it means this is the optimal value over all separable measurements. So we just first begin with one observation that for orthogonal states, this probability of success and separable fidelity are equal. And this has nothing to do with whether the measurement is separable or not. For any set of orthogonal states, the separable fidelity equals, the fidelity equals the probability of success. In particular, when I consider the set of separable measurements, the probability of success equals the separable fidelity. But when you have non-orthogonal states, and that's something very important, when you have non-orthogonal states, the probability of success is different from separable fidelity, and they tend to diverge from each other. More non-orthogonal the states become. And I will present an example to illustrate this effect. So we begin with, so now we present this bounds on separable fidelity. So we start with the lower bound, and this lower bound is pretty easy to obtain and is very intuitive. And so consider this set, pi psi I, once again this state psi I occurring with probability pi, and consider the collection of all subsets that are perfectly distinguishable by separable operations. So I am given a set, right? And I'm only interested in the subsets. I just find all the subsets that I know can be perfectly distinguished by separable operations. And R is this collection of all such subsets S, X. So X is a subset such that separable fidelity is 1. And Px be the a priori probability that a state selected from S belongs to the subset X. So that's the probability, a priori probability. And this result tells you that the separable fidelity is lower bounded by the maximum of all such Px's. Okay, and there's a very easy way to see why it works, because we know that the separable fidelity is lower bounded by the success probability. They're equal when the states are orthogonal. Otherwise, success probability is less than or equal to separable fidelity. Second, once we know that we are in the set X, and we know that it can be discriminated exactly, then for the particular set, the fidelity is 1. Often we are interested in the situation when the states are equally likely. And in such cases, there is a very simple bound, that is the separable fidelity is lower bounded by this quantity, where M is the maximum size of the subset S. That is, you take all the subsets that are perfectly distinguishable by separable operations, and M is the subset for which the cardinality is the maximum. So let's get to some upper bounds. So here what we have, once again we have these states, and suppose that square root of lambda I is the largest Schmidt coefficient of the states II. If that's for any such, for every state you can always have that. And then the separable fidelity is bounded by this quantity. And this is the usual operator norm that is the largest singular value of this. Now when the states are orthogonal, it's easy to see that this is simply the maximum of this quantity is pi lambda I. What you should note here is that when the states are sufficiently non-orthogonal, then sometimes this bound is not good because it's not informative, because it gives you a value larger than 1. So there are some interesting corollaries which actually generalizes and strengthens some earlier bounds obtained before. So for instance, when I have a set of an equally likely orthogonal states in D1 cross D2, then the separable fidelity is bounded by this quantity. Is greater than 1 over D2, then the state is not distinguishable by losses, by separable operations. Here is another result. This is a bit, the proof is not so complicated, but it kind of looks complicated bound on probability of success. Now we know that since probability of success is always less than or equal to separable fidelity, so any upper bound on separable fidelity is also on probability of success. But the converse is not true. So that's why we have this result separately, which gives you an upper bound on the probability of success for a fixed measurement. And for orthogonal states, this is also an upper bound for separable fidelity. And this turns out to be very useful. So I will give you some examples to show that when these bounds are optimal. So I will begin with that example Navascu considered in his paper in 2008. So he considered this case of 4 Bell states where the Bell states occur with probabilities pi in such a fashion. And numerically he computed the fidelity to be P1 plus P2. But this can be obtained analytically using the bounds we have derived here. Theorem 2 gives us the lower bound because any 2 Bell states can be perfectly distinguished, and you cannot perfectly distinguish more than 2 Bell states. So this gives you a lower bound, and from theorem 4 you can get the simple upper bound. So which gives you exactly the separable fidelity for Bell states. And this is simply an extension to show that how these bounds can be applied to a multipartite system as well. In this case also, you can show that the separable fidelity, when all A, B, and C are separated from each other, is P1 plus P2. This is an example where we have a set of 4 orthogonal states in 2 cross 2, but they're not maximally entangled, but the Schmidt coefficients are all the same, that is, they're all equally entangled, but not maximally entangled. In this case, corollary 2, which gives an upper bound on the separable fidelity, tells us that it's bounded by alpha square. Now you can simply see that simply by measuring in the computational basis and do a trivial, sort of trivial decoding map, the achievable fidelity turns out to be alpha square. So
is greater than alpha or beta?
Alpha is taken to be beta, greater than beta. So far, we have shown the optimality of the bounds considering only orthogonal states. Right. So you might wonder whether these bounds are really optimal for non-orthogonal states. And here's an example where I claim that the bounds are optimal also for non-orthogonal states. So this proof is kind of involved, so I'm not going to get into that. You can find that in the paper, or I can discuss with you later on. So I will just simply mention that, the result. So I have a set of 4 states here, and they are non-orthogonal. Right. As you can see, psi 0 and psi 3 are non-orthogonal. So I have this case where each maximally entangled state occurs with probability P, and the product states occurs with probability Q 1 minus, which is equal to 1 minus 3P. Here, so you can see if I just measure, look at the states, and you can easily see that if I measure in the computational basis, I can always distinguish the states except when the outcome is 0, 0. Except when the outcome is 0, 0, then the state could be either psi 0 or psi 3. Then you choose the maximum likelihood answer, and then you can show that then you can get a lower bound on the probability of success. And then by applying theorem 4 and do some calculation, and you can show that it's also an upper bound. And this is my final slide, and I want to emphasize that for non-orthogonal states, this distinguishability measures that we consider, probability of success and separable fidelity, they can give very interesting observations. You can get really interesting results here. So here I have two sets. The first set consists of orthogonal states, but it's locally indistinguishable. This one, the states are all orthogonal. Here, they are not. Actually, they span a two-dimensional subspace. They live in a two-dimensional subspace, and they're linearly dependent. You can easily compute for the first state, the probability of success must be equal to separable fidelity because the states are orthogonal, which turns out to be 3/4. For S2, that is more interesting, separable fidelity is 3/4, but probability of success is 1/2. Then what does it mean? So here I have two sets of states which have the same separable fidelity, but one has smaller probability of success. So what kind of conclusion you can draw from here? They're equally distinguishable, or equally hard to distinguish, equally easy to distinguish. This one is more distinguishable, this one is less distinguishable. So we have to understand what these measures actually quantify, what exactly they are trying to capture. For orthogonal states, you cannot make that distinction. But when you go to the region of non-orthogonal states, then you can see what's happening here. The separable fidelity, in some sense, is a truly quantum quantity. Right. And when the states are close to each other, sufficiently close to each other, so it kind of enables approximate cloning easier. And that's why the separable fidelity goes up for the second state. But when the states are close together, then the state identification becomes hard. And probability of success being a classical quantity reflects that fact. And that's why probability of success for the second set is 1/2. So that will be all for now. And thanks for your attention. And this is Michael. He's not here.
Could you go back to the definition of the separability fidelity or separable fidelity?
Sure.
The guessing strategy, do you demand that that is also separable? I'm assuming that's a separable operation.
No, guessing strategy is simply a map. So
Sorry?
I get an outcome A,
Yeah.
and based on that outcome, I simply prepare a state, or I simply guess a state. Which
Sure,
is phi A.
but they're bipartite states, right?
When I restrict myself to separable measurements, I just simply guess a bipartite state.
Sorry.
Phi A.
Say that again? Sorry.
I simply guess a state which optimizes this quantity.
Okay, so you're not actually envisioning it as a preparation of the state.
Right. In some cases, it's kind of weird that to optimize the fidelity, you need not guess a state which belongs to the set itself.
Compare it with the separable fidelity, FS. So if it is for more than one copy, would the probability of success would reduce, I guess?
No,
so
with
if it is only one copy case.
With more than one copy, you expect to...
probability of success to reduce.
Right. No. With more than one copy, you expect things should get better.
Yeah.
Right.
So then what happens to FS?
No, this quantity should increase in principle.
That would also...
I suppose so.
Okay.
Okay, if there are no more questions, let us thank them. Together.